Today, I want to talk about CLOVA, a closed-loop visual assistant with tool usage and updates. Okay, and first, let me tell a little bit about abstract of this paper. Currently, AI is evolving really fast. Past 5 years, there were created a number of tools like ControlNet for stable diffusion, LLMs like Llama, vision models like GPT-4 Vision, and multi-models like GPT-4o, where O stands for Omni multimodality. Okay, and the researchers are exploring the potential of utilizing large language models to develop robust visual assistants. However, many current methods freeze the tools, hindering their ability to learn continually and adapt to new environments, like we are people. To address this issue, the researchers from different research universities, including Peking University and Chinese University, introduced CLOVA, a closed-loop visual assistant. CLOVA operates within a framework that includes three main phases: inference, reflection, and the learning. In the inference phase, large language models generate programs and execute corresponding tools to complete the tasks. During the reflection phase, a multi-model global local reflection and schema analyzes the human feedback to identify which tools need updating. And the learning phase employs three flexible approaches to automatically gather training data, and also introduces a novel prompt tuning schema to update the tools, enabling CLOVA to acquire new knowledge efficiently. And experimental results show that CLOVA outperforms existing methods like by 5% and the visual question answering, and 10% in knowledge tagging, and 20% in image editing. Table of contents, we will talk about the background and the new methods. Multimodal agents like end-to-end models via visual instructions like Lava, Mini GPT-4, GPT-4 Vision, and also tool-based models via large language models, visual programming, visual chat GPT. For example, okay, as you can see in the image, there's a user query, and it asks like, please generate a red flower conditions on the predicted depths of this image, and then make it like a cartoon step by step. And as you can see, there's a prompt manager that sends to ChatGPT, and there's iterative reasoning, and the right side there's a visual foundation models like Bleep, Stable Diffusion, and ControlNet. And then after iterating the reasoning and multiple iterations, you can see the output. Okay, but there are a number of problems that may occur with multimodal agents. For example, as you can see in the slide, I highlighted the three problems with one of the tool-based visual programming, or VisProg. When we prompt the model, take the director of the movie Parasite on the left side image, model takes the wrong person. In short, model cannot recognize the Bong Joon-ho. Who is this person? And the second, in the middle image, when we prompt the model to replace Leonardo with Dominic Sadosh, model places with wrong person. In short, model cannot generate Dominic Sadosh. And in the third, on the right side image, when we ask the model whether a provided image has windmill in the upper part, it replies with no, which is wrong. And last but not least, the research shows that the current tool-based models via large language models cannot learn new knowledge and always fails on similar phases. Now, as you can see, there's a new method, CLOVA, a visual assistant that can self-improve within the closed-loop learning framework. And there's three main phases: inference, generate a program, and call visual tools to solve the task, and reflection, identify which tool is problematic, and the learning, to automatically collect training data to update the tool, and it will loop again to inference, reflection, learning. And there are toolkit, for example, location, crop, seg for segmentation, visual question answering, and replace for replacing, and select the specific region or the border. And then CLOVA improves the VisProg, or visual programming, by first generating the plans using LLMs, which are then used to generate programs. This intermediate planning enhances both inference and the reflection phases. And CLOVA selects examples from a demonstration pool For example, D, which includes both correct and incorrect examples, which critiques. These examples help in creating effective prompts for large language models. In the plan generation, the demonstration pool is structured with correct and incorrect examples for both plan and program generation. And the features from the task instructions and examples are extracted using the BERT model. Similar examples are combined with instructions to create a prompt for large language models to generate plan in a single stop. And the program generation, correct and incorrect program examples are combined with a plan as a prompt. Large language models then generate the programs in a single step. For example, as you can see, program generation based on the plan generation, and the tool executions after program generation. And the tool execution, CLOVA activates tools from a toolkit from 15 tools, including the neural networks and the Python functions to execute the tasks. For example, there's a log, tools log, that tools to be updated for object localization. For example, visual question answering uses the BLEEP model for visual VQA. And for example, for classify, there's uses the clip model to classify the given image, or replace the uses the stable diffusion in painting model to replace one object with another desirable objects. And there's some function, for example, eval. It's a Python function to process the string expressions for answers. Like you write a function or statement as a string, it will just evaluate. And the reflection, if a task is not solved correctly during the inference phase, the multi-model global local reflection schema uses LLMs to generate critiques, identifying which tool needs updating. For example, result conversion. Large language models struggle to identify errors independently. So human feedback, wrong results, and intermediate results are provided to help pinpoint error sources. Visual results are converted into text using the BLEEP model, captions the images, and a global reflection. CLOVA first uses global reflection to generate critiques in one step. Prompts include task inputs, feedbacks, and generated plans and programs and intermediate results. These prompts are sent to large language models to generate critiques that inform tool updates during the learning phase. And last, and the local reflection, if CLOVA still fails after global reflection and the learning phase, local reflection analyzes each program step. Prompts include task inputs, feedback, checked steps, and the current step needing review. Each step includes plans, programs, and intermediate results. Prompts are sent to large language models to infer if the current step has errors and the reasons for them. And the local reflection continues until the error location and the reasons are identified for a specific step. And there is a learning phase, for example, data collection, training, and the validation. After identifying the tools that need to be updated from the reflection phase, CLOVA then moves to the learning phase to collect the training data and goes through the training, validation, prompt tuning to update the tools. For example, in the data collection, we explore the three manners to collect data. First is using the LLMs to generate training data for the visual question answering tool. And the second, from open vocabulary visual object grounding datasets for the log and the seg tools. For example, if the reflection phase indicates that log doesn't work well for the visual concept, for example, horse, CLOVA will select images and bounding boxes of horses from the LVs dataset to update the log. And the third, searching on the internet for the select, classify, and the replace tools. For example, if the classify is still marked as unable to recognize the horse during the reflection phase, CLOVA will search the internet for images of horses to update the classify. Let's talk about the prompt ensemble. For example, identify visual concept and a new instruction. We give the image, replace the dog with the cat, and we will use the tools seg, select, and the replace. For example, seg, segmentation the dog from the image, and select the dog and the replace with the cat. that dog. Each tool has its own prompt pool, and as you can see, sum of prompt vector for the same concept is cosine similarities between the features. A little bit about experiment that researchers made on the research CLOVA. For example, compositional visual question answering, GQA dataset, and with 500 samples from the training split for training and 500 from test development split for testing, and with top one accuracy metrics. And the second, multiple image reasoning with a different dataset and with different tasks. Judge if a statement above two images is true or false. And the plan and program generation, the prompt contains the 4 correct and the 4 incorrect examples, and the demonstration pool will be initialized with about like 20 in context examples. And the language guided image editing, the images was collected manually, and on the image editing task, they used like 129 images with 193 instructions, and the training data had 27 images with 78 instructions, and the remaining part is tasting data and evaluated manually. And the factual knowledge tagging, they used the 86 images with 177 instructions with 10 images with 88 instruction in the training data, and the remaining is tasting data with the F1 score metrics. Here you can see the main results: 4.8% improvements on GQA datasets, as you can see in the CLOVA, and 4.9% improvements on the NLVR V2 dataset here, 65.6, and 20 improvements to image editing, and the 10% improvements to knowledge tagging at all. And some qualitative results they shared on the research. For example, there was a lot of like qualitative results. As you can see, there is instruction replace the bird with pine gross beak, kind of some passivity forms. And there was a human feedback. The pine gross beak as a new generated image is wrong. And then, as you can see, there's generated program and intermediate steps. Critique, for example, error location, functions called by programs. There's a main error and it says reason. And the step 3 of the program here, the used function replace failed to generate a pine gross peak to replace the bird. The replace function needs to be updated. There's a reason and there's a very similar like location error. And then it corrects it. As you can see now, it works correctly. After the critique and updating the tools and looping until they have the correct results. There is also some example of reflection for the large language models in visual question answering, like it says what it says. What do you think is the item furniture in the lamp made of glass is sitting on? And there is all wrong answer dresser. Human feedback, the answer should be shelf because it stands on a shelf. And then there's a generated program and intermediate results based on this. There's a generated critique, and after generated critique, the model will update the tools, update the program and the plan, and then it gets the right answer. For example, as you can see here, have the crop, and then there is a crop below. It updates. Yeah, the research also showed some ablation studies for reflection prompt engineering for LLMs and prompt tuning for visual tools. And it says, like, as you can see in the table, the global reflection, the local reflection, and correct, incorrect examples are necessary because the results are higher than without these cases. And also, there is 21% improvement on GQA dataset, 13.8% on the NLVR V2 dataset. What else? Large language models, simple large language models like Llama, Mistral, outperformance original ones when it used with the CLOVA. As you can see here, there was 39 and there's 60. Initially, there was 20, and while we use the CLOVA, like combined the Mistral with CLOVA, there's a 31 or 42. it increases. I will share the presentation. You can check the supplementary materials. There are a lot of interesting things. And yeah, actually, that's it. Yeah, I think it was understandable. If you have any questions, please ask.